Hello, everyone. This is the third part in a three-part series on coordinate systems. The first one was Cartesian coordinates. Then we did cylindrical coordinates. Now we're going to do spherical coordinates. There's actually a lot more coordinate systems. There's hyperbolic, elliptic, things like that. I'm not really touching on those, but certainly if you go further, say in astrophysics or something like that, there'd be some very useful coordinate systems when dealing, for instance, with planets in elliptical orbits. There's parabolic coordinates, all sorts of cool stuff. But anyways, I just want to finish up with the spherical coordinates again. So we'll have some unit vectors that we can use, just conceptually use them, not necessarily calculate them, but I'm going to calculate them and all that good stuff too. So let's go ahead and get started. I'm going to turn it on my document cam. So I've already got a XYZ coordinate system set up, and I do have it such that it's in that right-hand frame, meaning the X coordinate. If I took the I hat and crossed it with the J hat, the result would be the positive K hat. That's crucial. If you don't have that, then dot product or cross products and things like that can get screwed up. So you always got to have a right-hand coordinate system. Frankly, I don't know how easy it would be to recover if you use a left-handed coordinate system, so I've just always stuck to a right-hand coordinate system. So again, I told you before that if you extend your right hand, you extend your index finger, and then you turn your middle finger perpendicular to that, and then your thumb, of course, perpendicular to both of them, then your index finger should point in the positive X direction, your middle finger should point in the positive Y direction, and then your thumb will point in the direction that the positive Z axis should be. So that's what we have here. So what I'm going to do is start with considering just a point P. So let's say this is our point P. I'm going to label it P, and then up here I'm going to write that P could equal X, Y, Z. That's a typical way of referring to it, and I'll actually draw what those X, Y, Z's are, and then I'm going to show you the other coordinate system. So first off, I'm going to try to figure out how tall or how big Z is and how big X is and how big Y is. So I draw a little line down here. And of course, I go back to here, and this is the rho, or what I'll call rho now. But in the cylindrical coordinate system, I called that R, but we're using R for this spherical coordinate system. So in this case, I'm going to call it rho. Now, if I draw a line perpendicular or parallel to that one, that should give me the Z coordinate, which you can see is right here. So that's the Z for that point. Similarly, if I draw a line parallel to the Y axis, where it strikes the X axis will be the X coordinate. So I go from here over to here. There's the X ordinate, if you will. And similarly, if I draw a line parallel to the X axis until it hits the Y axis, then that will give me the Y, which used to be called I think the X was the abscissa and the Y was the ordinate. So here is the actual Y value. So we could specify this point by saying it's, X number of meters from the origin, Y number of meters from that point, and then Z number of meters up from the XY plane, and that will work fine. But now I'm going to introduce a new coordinate system, and that coordinate system I'm going to use the green color for, and that coordinate system will be R, theta, which is the same theta from cylindrical coordinates, and phi, which is a new one. Okay, some people pronounce that phi, by the way. I've always pronounced it phi. I'm not actually sure what Greek people would call it, but anyways. So when you look at this, if you draw this line over here from rho, which I'll write as actually I'll write it in blue so nobody confuses it for a actual coordinate. I'm going to call that quantity right there rho. But if you measure the angle counterclockwise from the positive x-axis to the line rho, you'll get the angle theta, which is in fact the theta coordinate system. So that are the theta coordinate. Now, if you draw a line from the origin out to the point P, that will actually give you the spherical coordinate R. So that distance right there is R. Okay. So that distance is r, this angle is theta, and then the last coordinate is the angle phi, and we measure that down from the positive x-axis, or excuse me, positive z-axis. So that angle right there is phi. So those are our three coordinates, r, theta, and phi in that order. And a given point could actually be stressed if you actually use the r hat vector. You could actually just express it as the distance r times the r hat vector, because the r hat vector, you'll see, turns out to be a function of theta and phi. But in general, if you want the coordinates, you have to do r, theta, and phi. So let's start off with looking at our unit vectors. So a unit vector is basically what we call a directional derivative. So it's a directional derivative in the direction of the coordinate change. So if I imagined a vector r, which equals, r times r hat, which r hat depends on theta and phi, like I told you, then if I take the derivative of that vector r with respect to r, I'd get the r hat vector. Similarly, the derivative of r vector with respect to theta, I would get the theta hat vector, a unit vector. Of course, you have to unitize it yourself when you do it that way. And then finally, if I took the derivative of r with respect to phi, r again, the vector with respect to phi, and then divide it by that magnitude, I would get the actual phi hat vector. But I will draw them here. So if I just continued this green line that points radially from the origin through this point P, that would actually give me my unit vector r hat. And I made it kind of big so I can draw it a little better. Now, if I went in the direction of increasing phi hat, you see that would be this way. It'd be perpendicular to this r hat vector, but it'd be in the same plane as this rectangle is here. So I'm going to try to draw it perpendicular to this guy, and about the same length. So I'm saying it's going to be roughly that length. That would be phi hat vector. And then finally, the theta hat vector is perpendicular to both of those, but it's actually the exact same theta hat vector we had in the cylindrical coordinates. And in fact, that's going to be roughly perpendicular to this line. So I'm going to draw it like this. So this would be my theta hat vector. So those are our three unit vectors. Let's go ahead and work out what they are. So if you want to do that, we sort of need to draw another coordinate system. So I'm going to draw another y-axis like this. I'm going to draw another x-axis like this. And I'm going to draw another z-axis like this. So this is x, this is y, and this is z. Okay. Now, to get that r hat vector, I need to find its x component, y component, and z component. So I'm going to start off by drawing a line parallel to the z-axis until it hits the xy plane. And then I'm going to make a line that's sort of the same as rho. So it'd go like this. So that actually helps me make sure I drew it the right length, for instance. Okay, so I think you can see now that this right here is the z component of the r hat vector. So I can write down here r hat is equal to, and I need an x component, a y component, and z component. I now see the z component. This is r hat sub z, for instance. Now, if I draw a line parallel to the y-axis over here and run it into the x-axis, that will allow me to determine the x component of r hat and the y component of r hat. So the x component, remember this angle right here is just theta again. So that angle's theta. And this angle right here, let's not forget, is phi. Okay? So if you want the x component, first off, you got to find this component down here, which might not be that obvious, but if I draw this other blue line, I think it'll make it a little more obvious to you. So you see this triangle right here. This is one leg, then this is perpendicular to it. That's another leg, and then this is the hypotenuse. The hypotenuse is the vector r hat. And if you take the sine of that, you get opposite, which is this guy, over hypotenuse, which is 1. And this guy is actually the projection. It's the same as this sort of row that we did for the point, but it's the row of the r hat vector. So I first have to find the component of r in the xy plane, which is this guy. So I've got to multiply by sine phi to get that. So I'm going to put sine phi down for my x component. I know that's got to be in there because that just gets me to this line. Now I take the cosine of theta, because cosine theta equals this, which is the x component, over this, which is basically r sine theta, or excuse me, r hat sine theta. So now I got to take cosine theta, and that's my x component. Now the y component is done similarly. I have to again project it down into this plane. So again, using the sine function, I do sine of phi. But now, instead of wanting this part, I want that one, which is given by sine theta. So I say sine theta, and then put a j hat after that. So that's the first two components. Now the final one is actually the z component, which is kind of hard to see here, but if you look over here in this little triangle, you see cosine is equal to adjacent, which is z, over the hypotenuse, which is 1. So I can just call the component, the z component, just cosine phi. And that'll be in the k hat direction. So that is my vector. Now you might be skeptical about the size, but I'll tell you it's already in a unit size. So let me show you what happens here. If I first take and try to find the length of r hat, the first thing I'd like to do is find the length of this, which I think you can tell is the x component squared plus the y component squared. So I'd get sine squared theta, cosine squared theta, or excuse me, sine squared phi, cosine squared theta, plus sine squared phi, sine squared theta. I could factor out the sine squared. Now I take the square root of all that. That sine squared that I factored out just becomes sine theta, but the cosine squared plus the sine squared that's left just becomes 1. So I end up just getting sine theta as the magnitude of this guy. Okay. Now I have this guy and this guy, the z component, which is this one over here. So we found out this one has a length of sine phi. This one has a length of cosine phi. So when I take the magnitudes, I do sine phi squared plus cosine phi squared. That's just 1. Take the square root of that, I get 1 again. So clearly this thing is already a unit vector. We need not do it again. Okay. Again, if you were to calculate this from the r vector, you could get it as well, but in that case, you'd get it as a vector with a magnitude r. So then you'd have to divide it by the magnitude of the vector, and that would actually just give you the exact same thing because it ended up just cutting out the r because that's the magnitude of the vector. Now theta hat, we don't really have to go through the drawing here because theta hat's still the same theta hat it was in cylindrical coordinates. It still lies in the xy plane, so it only has an x component and a y component. And in fact, if you want me to draw it, let me draw it this way. I will use my little ruler, my trusty ruler, and draw this as sort of rho hat, if you will. So that's sort of the rho hat vector, because now we're calling that variable rho. Now 90 degrees ahead of that is in fact the theta hat vector. So actually I should draw that one with red. So the theta hat is roughly this way. And you can see that this is parallel to the y-axis. So I can draw it this way. And this, of course, is parallel to the x-axis. So it's a little bit different than this. So this is my x again. This is my y again. Now, this angle right here has to be theta. And what you realize then is since this angle from here to here is 90 degrees, and this angle from here to here is 90 degrees, then clearly this has to be the angle theta as well. So with that in mind, you want basically the y component and the x component. This would be your y component, which is in the positive direction, and this would be your x component, which is in the negative direction. So you'd end up saying, okay, well, here's my theta. Cosine gives me the adjacent, which is the y component, and sine gives me the opposite, which is the x component. But I got to remember it's negative, so I say sine theta I hat plus cosine theta j hat. So that's our unit vector in the theta hat direction. Notice it is exactly the same form that we had in the cylindrical coordinates. Now, the final one is the rho hat, but I think that's maybe a little confusing for you guys in general. Remember, this is r hat, and then another 90 degrees in front of it, that is phi hat. So we can sort of do the same thing and realize that from the xy plane, this angle is phi. So I can put that in here and realize from this little rho vector, if you will, that angle is phi. So what I need to find the components of phi hat is I really need to find the component in the xy plane, i.e. like the rho component, if you will, which would be right about here. And I think you can see when I take the cosine of phi, that gives me the rho, and then I'll just take cosine of theta, and that'll give me the x. So if I want to actually do theta hat, or phi hat, excuse me, the phi hat vector, again, we're just going to trust that it turns out to be unit-wise, and it will. So first off, I got to take the projection of theta hat into the xy plane, which is gotten by taking the cosine of phi. So I'm going to say cosine phi. And then now that I'm in there, I got to take the cosine of theta, and that will give me the actual x component. And you can tell it actually does have a positive x component, so I don't need to mess with the sign or anything like that. So I'm going to say this one's going to be cosine theta. And that would be I hat. Similarly, when I do the y component, I do, again, cosine phi. The y component of this does appear to be positive as well, so I don't have to mess with the sign. So I do cosine phi. But this time I got to take the sine of theta. So it'll be sine theta. And that'll be multiplied by j hat. So that gives me the x and y components. But then finally, the z component is negative. So I'll write a negative there. And then I just realized to get that, all I got to do is take the sine of phi. And that will give me this one, because the sine of phi is opposite, which is the z component, over hypotenuse, which is supposed to be 1. So I'm just going to call this sine phi k hat. So that is, in fact, the unit vectors for the spherical coordinate system. And they can come in really handy. Again, as you can tell, like with the cylindrical coordinate systems, these unit vectors are functions of positions. They actually change as a function of position. So when you do calculus on them, whether it be a dot product or a cross product with a derivative or an integral or just a straight derivative, you have to take the actual derivatives of the r hat vector, the theta hat vector, and phi hat vector all by itself. In fact, in engineering dynamics, you'll learn a lot of neat new equations when you're in a rotating coordinate system, and they come specifically from knowing how to do this. So that's our spherical coordinate system. Now I want to talk about what the individual differential volume area elements and the differential area elements are. So I'm going to turn to another coordinate system that I drew just to keep that one from getting so cluttery. So now if I take and consider a point again, what I'm going to do is now consider, changing those variables by a differential amount again. And I'll take a point, say right here. And let's say it's connected by the line, the radial line R. All right. And then I'm going to say this is R, but I'm going to extend it a differential amount dr. So I get a quantity like this that's just dr. So this is R from here to here. This is dr. So the whole thing's length is R plus dr. Now, if I wish to, I might want to first consider changing phi hat. So right now I'm saying this angle right here, I said say changing phi hat, I mean changing phi. This angle right here is phi. If I allow that to go a little bit further, then I will get a change in phi of d phi. So now this little angle right here is d phi, but that distance from the R here and the R here is actually an arc distance. So we have to use again S equals R times theta to realize that this distance is R d phi. Okay, so now I have one unit of area dA, and I'll call that dA R phi, and that's equal to plus or minus R dr d phi. That's the magnitude. Of course, you have to draw down here to realize this, so I will do that real quickly. Let me do it with a blue line. Okay, so that gets me that. This gets me our normal row, if you will. So when you see that, you can see, oh, okay, so this thing clearly would point in perpendicular. In other words, when we want to represent this differential area element as a vector, we would want it perpendicular to this plate, this little sort of rectangular thing. So that has to be in the phi hat direction, or excuse me, the theta hat direction, or the negative theta hat direction. So I'm going to write it right here as theta hat. Notice that's the variable that's left off. That's sort of the pattern that you should have seen by now. Okay, so that's when you change R and phi. What about if you change R and say theta? Well, when you change R and theta, then you get something slightly different. So changing theta, remember, has to happen down here in the XY plane. So I'm going to draw this with another green and say this angle right here is d theta. Okay, but again, that can't be the arc length because the arc length can't have units of radians. It's got to have units like meters and stuff. So I'm changing the R, which I'll bring this down from here again. Let's see if we can do this properly. So this distance out to here is R. This distance is dr. And then I have this little arc right here and this little arc here. Now this, because this is d theta angle, the actual distance has to be the radius, but it's not really the radius now, nor is it exactly dr. Notice I projected dr, which was a little longer. So I'm just taking this part right here, which actually differs by an amount of sine phi. So I actually got to say this is not dr. This is dr times the sine of phi because I had to project that dr down into the xy plane. That also means that this right here is not r, this is r sine phi. Okay, so this thing is not r d theta, it's r sine theta, or excuse me, r sine phi d theta. And this side right here is actually, if I wanted it down here, it'd be r dr times the sine of theta. But in fact, I need it to be up here, not the projection. I just needed this radius so I could make this correct. So now I'll draw it back up in space again. I'll try to draw it like this. And I'll try to draw it like this. So what we're going to get is this little guy turning off like this, okay? So the radius of that arc was r sine theta, but this part right here will still be dr. So the actual differential area element for this one, this is dA, such that we allowed the two variables r and theta to change. It's going to equal, again, plus or minus, but in this case, it's going to be r sine theta, excuse me, r sine phi, times dr, and then times d theta. And that's all pointing in. Of course, now you can see it's going to be perpendicular, so that's actually in the phi hat direction. Again, it could be this way or this way, but again, notice it's just the variable that we didn't use. So we now have a differential area element for that one. The only one we have left is allowing dr and, or excuse me, allowing phi to change along with theta to change. So when phi changes and theta changes, I think you can see you're going to get this little bit right here. So that face right there, okay, which can be represented by this little line going back to here, and this little line going back to here. So again, the change was d phi, so this side right here would be r d phi, and this side right here would be r sine theta d phi, or excuse me, d theta. So we finally have dA, and this time it is theta phi vector is equal to plus or minus again. As I said, this was r d phi, and this one is r sine theta d phi, so this is r squared sine phi. I think I said sine theta a second ago, sorry about that. R squared sine phi d theta d phi, and pointing in the r hat direction, which I think you can see is pretty obvious. Okay, so putting all those bits together, you can actually get a differential volume element too. But you also might notice, check this out, this one has r times dr, so that's like r squared, in other words, meters squared, and then times some radians. So yeah, this has units of area, just like this one does, r dr. Both of those are like meters, so that would be dA is in meter squareds again. Remember, radians technically don't have any units. They come from this, which is theta is S over R. That's like meters per meter, so it has no units. And then finally, this one only had angles until we had that r squared, so that's gives us another correction as well. So we see, in fact, that the differential area elements are actually consistent with the units that we'd expect. So we see here this little wedge of a cube, or a wedge that's sort of shaped like a rectangular solid, but of course this wedge has an arc on the back that's curved like that. It's got a flat spot on here, but then it's got an arch like this on the front, and then an arch like this on the inside. So it's a little bit different, but again, if you actually worked out the math, you would find that the difference between this and a actual rectangular solid are of the order of dr cubed, r dr d theta, d theta cubed, d phi cubed, and so on and so forth. So they're actually at least third order in differentials, and since you take the limit as the differential goes to 0 to do an integral, it's certainly okay to deal with that. So now let me go ahead and write the differential volume element, treating it just like it is, in fact, a cube. We know that this side right here is r d phi. We know that this one right here is r sine phi d theta. And we know that this one right here is just plain dr. So it should be r squared r squared, and I'll go ahead and add the sine phi. Sine phi dr d theta d phi. That is our differential volume element, which I can use to do a quick integral to integrate and find the actual volume of a sphere. You could use, for instance, this differential, no, not that one. This differential area element, that's the front area element. That's the one whose r hat's perpendicular to it. You can use that differential area element to find the surface area of a sphere as well. But I'm going to do the volume just to give it a little try. So V is equal to the integral of dV, which is going to be the integral from phi equals 0 to pi. That's the big thing. Phi only goes to pi, because if it did, it's, you know, a phi this way would be the same thing as that phi minus 180. So you just get the same, or actually I said that a little backwards, but I think you understand what I'm saying. The other integral, theta, is going to go from 0 to 2 pi. And then the r is going to go from 0 to r. So I'm talking about a sphere centered on the origin here. And that's going to be r squared dr. Now I'm splitting it up. Then it's going to be d theta. Then it's going to be sine phi d phi. Okay? So when I do this innermost integral, that's going to give me 1/3 r cubed. 1/3 r cubed evaluated at r is 1/3 big R cubed. Evaluated at 0 is 0. So I get 1/3 r cubed. That's nice. Okay. Now I still have this part of the integral left. Notice the only thing that's missing is the r's. Now I'm going to integrate d theta from 0 to 2 pi. And I think you can see that the integral of d theta is just theta. And when I evaluate at 2 pi, I get 2 pi. When I evaluate at 0, I get 0. So this becomes just plain 2 pi. And then finally, now I've evaluated everything but this one. Okay, so I got the integral of sine theta d phi. We know that the derivative of cosine is negative sine. So the integral of negative sine should be cosine, and therefore we say that the integral should be negative cosine. So the integral of sine phi d phi should be negative cosine phi. Negative cosine phi at pi, cosine of pi is just -1, but the negative of that would be +1. And then I'm going to subtract from that the negative cosine of 0, but the cosine of 0 is 1. So the minus a -1 gives me +1. So I end up getting 2. So ultimately, I got 2 for that last integral, and lo and behold, that's correct. I got 4/3 pi r cubed is the volume. So I think that covers just about everything for the spherical coordinate system. I hope that this will help you, and I hope you can have some fun playing with it. Have a good day.